Now that we've learned how to apply Thevenin's theorem to a circuit, let's look at a few more examples to kind of illustrate some of the subtleties of nodal analysis and when you apply it to Thevenin's theorem. And also to look at some things about Thevenin's theorem that may not necessarily be obvious at first glance. So here we have an interesting circuit, and I want to find the Thevenin equivalent for it. And in this case, notice I've got two halves of the circuit with a single wire connecting them. And one of the questions I always like to ask people when they see something like this is, what is the current in that wire? That's a good question. And let's think about this from a KCL point of view. Kirchhoff's current law holds at every level. And so let's say we've got one circuit block here and one circuit block here. So it doesn't matter whether it's one node, multiple nodes, or even a fraction of a node, what goes in must come out. So here I have a dividing line between this part of the circuit and this part. This current is going into that block. What does KCL say? Well, if I call this current I1, I1 is going in, nothing's coming out. So in this case, I1 must be equal to 0. So when you see a single wire connecting two circuit blocks, by inspection you know that wire is zero. That wire has 0 amps flowing through it. So the question is why do we have it? Well, we're drawing this wire all the way across because it gives us a common connection if we want to put a ground, which is exactly what we're going to do for this node B. So let's go through and let's do that, and let's solve for this circuit. Now this circuit is also interesting because this type of topology we see here is actually rather familiar in the sense that you will see a lot of amplifier topologies. If you ever, for example, take a class in electronics, you'll see transistor amplifier circuits that can look very similar to what we see here. So let's go analyze this and let's see how this works. So in this case, what we're going to do is, first, I've got a current I1, which is the dependent source variable for that current-controlled current source. The voltage V1 across this 25 ohm resistor, I've got 3 V1. I have a voltage-controlled voltage source. So let's go through and let's solve for this. And in this case, I'm going to ground the bottom. Once again, I like to do that because then if I define VOC between terminals A and B, then by definition, the voltage of that node must be equal to VOC, which incidentally must also be equal to V1. VOC and V1 are clearly the same voltage. So in this case, I've got 3 V1. That's actually equal to 3 VOC. And since this is a defined node, this must be equal to 3 VOC. So now, I note over here, this is 5 volts. This node is defined. That node is defined. There really isn't a KCL equation we can write here. There's not one we need to write. Over here, I've got the voltage V1 defined across this 25 ohm resistor, so of course I'm going to draw the current that direction and follow the passive sign convention for that resistor. So in this case, what I will have then is 20 I1 plus VOC over 25 must be equal to 0, and that is the KCL equation at this VOC node. I don't have to write any kind of dependent voltage source or any type of KCL equation over here because of that dependent voltage source. And both those nodes are defined, but I do need a dependent source variable. My dependent source variable is I1 is equal to 5 minus 3 times VOC divided by 2,000. So it turns out, as weird as that circuit looks, it's actually fairly simple to analyze. 2 equations, 2 unknowns, and if I solve, what I'm going to get is that VOC, which is equal to VTH, will be equal to minus 5 volts. So it's certainly possible for a Thevenin equivalent voltage to be a negative value as well as a positive value. Now let's do my RTH calculation, Thevenin resistance. Well, if we do that calculation, I've got this source I'm going to zero out. I've got dependent sources in the circuit, so clearly I need to apply source driving. So let's go ahead and do that. And I'm going to use the 1 amp current source, which means I need to find the voltage VT. Once again, this is a 25 ohm resistor with a voltage V1 across that resistor. This is 20 I1. This current is I1, 2K resistor, and this is equal to 3 V1. So in this case, with that 1 amp source, I know that by inspection, since this bottom node is ground, then this must be equal to VT, since I'm defining VT across this. But that means VT is also equal to V1. Clearly, they're the same voltage. And so therefore, this 3V1 must be actually 3VT. So this is a defined node, 3VT, and once again I can write the KCL equation at the output, and so 1 amp flowing in is equal to VT over 25 plus 20 times I1. That's my KCL equation. There's no KCL equation here, that's a defined node, but there is a dependent source and variable equation. And that is going to be equal to 0 minus 3VT over 2,000 is equal to I1. Again, I can solve, and if I solve this, what I'm going to get is that VT is equal to 100 volts, and therefore RTH is equal to VT over IT. IT is 1 amp, and therefore this is equal to 100 ohms. So there's my circuit. The Thevenin equivalent of that circuit will therefore look like this. Which incidentally, I could flip this and I could say that it's also equal to this. It's equal to 5 volts negative to positive between A and B. And there's our Thevenin equivalent circuit. So, interesting little circuit. Also interesting due to the fact we've got that minus 5 volts, and we can see we can turn that into a plus and by flipping the polarity around. Now, this also illustrates something else. I always have students ask me, Dr. Holman, why do you do VOC from A to B? Could you do VOC from B to A? Sure you could. You could calculate the open circuit voltage, in this case, from B to A, and what would you get? If you did that, you would get 5 volts from B to A. You get that answer. So in this case, it doesn't matter how you define the output VOC, the open circuit voltage, whether it's A to B or B to A, you're going to get the same circuit either way. It can be transformed into the other. So once again, these choices are kind of arbitrary. I just like to go A to B and usually ground the B node, but I could ground the A node and work it that way, and I would still get the same equivalent circuit. So always useful to point that out to people. Okay? Let's do another problem. And this is kind of an interesting problem because this illustrates something that's very fundamental to circuit analysis, especially when you're doing Thevenin's theorem. What if I wanted to find the Thevenin equivalent of this circuit? Okay, so I'm going to find the Thevenin equivalent of this circuit, which means first I want to find the open circuit voltage so I can calculate and determine the Thevenin equivalent voltage VTH. Okay, now this is an interesting circuit because you note this circuit has no independent sources in it. That's interesting. Let us go ahead and let's solve this. Let's try to calculate VTH. So in this case, I'm going to ground the bottom node. My top node will be equal to VOC. I'm going to call this node here, since I've got V1 here, then by definition that node becomes V1. The nodal voltage becomes V1. I'll just stick with that definition. And I'm going to pick these current directions. This one, I've got VOC, so I'm just going to stick with that direction for the current. And here I'm going to add this current between V1 and VOC. So for my V1 node, I'm going to have 0.01 V1 plus V1 over 100 plus V1 minus VOC over 50 is equal to 0. And for my VOC node, I will have V1 minus VOC over 50 is equal to VOC over 150. And I plug these equations into Mathematica, and I solve, and interestingly enough, I get that VOC is equal to 0 volts, and therefore VTH is equal to 0 volts. This circuit has a Thevenin equivalent voltage of 0. Now, the reason why I did this circuit is to point out something. It doesn't matter what circuit I draw or what circuit I give you. If there are no independent sources in a circuit, by inspection, all of the voltages and currents will be equal to 0. So this is just a general principle for linear circuit analysis. If the circuit contains no independent sources, all voltages and currents are equal to 0 by inspection. And that's worth writing down because it's very important. So by inspection, all voltages and currents are 0 if the circuit has no independent sources. Okay? What about the Thevenin resistance? Can it have a Thevenin resistance? No, absolutely. Let's go ahead and let's apply source driving. In this case, I'm just going to apply it to the original circuit. There's nothing in here to zero out. So in this case, I'm going to take the exact same circuit and I'm going to apply a 1 amp external source to it. I want to find VT. Now that node becomes VT in my circuit. Everything else is the same, and so in this case what I'm going to get is that 0.01 V1 plus V1 over 100 plus V1 minus VT over 50 is equal to 0. That's for my V1 node. For my VT node, I have that V1 minus VT over 50 plus 1 is equal to VT over 150. And now I solve, and what I'm going to get is that VT is equal to 60 volts, and therefore RTH will be equal to 60 ohms. So the Thevenin equivalent circuit for this original circuit is just this. A voltage source of 0 volts, a wire, and a 60 ohm resistor. So it is absolutely possible to have a Thevenin equivalent circuit which is nothing except a resistor. Along those same lines, it's also possible to have a Thevenin equivalent circuit that is just a source. So for example, what if you saw a circuit like this? And I asked you what the Thevenin equivalent voltage and Thevenin equivalent and resistance were. So in this case, the Thevenin equivalent voltage, VOC, well, just by inspection, that must be equal to 10 volts, right? Because the 10-volt source is across it. So that's equal to VTH. What about the Thevenin equivalent resistance? Well, I short out that voltage source. Now I've got a wire in parallel with a 10 ohm resistor. What is my equivalent resistance between those two nodes? Well, if I think of this wire as being a 0 ohm resistance, then it's equal to 0 in parallel with 10, which is just 0 ohms. So in this case, the Thevenin equivalent circuit is just this. It's a 10-volt source and nothing else. So you can also have circuits that are just sources, nothing else except a source. And you can have circuits that are nothing but a resistor. So this is absolutely possible, depending upon the configuration that you're examining. Now there's another question students will often ask. Is it possible for a Thevenin resistance to be negative? Yes, it is. With certain types of feedback configurations, depending on how the circuit is constructed, you can have a negative resistance. If you take a more advanced course in electronics, you will learn that the indication of a negative resistance results in a phenomenon called oscillation. Actually, a phenomenon called positive feedback, and results in oscillation of the circuit, building something called an oscillator. That's really kind of beyond the scope of a Circuits 1 course, but it's certainly possible. But also, having said that, if you ever work a problem, certainly on an exam, and you get a negative resistance, unless I warn you in advance that there is going to be a negative resistance, then you've probably done something wrong, okay? Certainly on exams that I would give, if I'm going to give you a circuit where you can expect RTH to be negative, I'll tell you, so you'll know it. Otherwise, if you get a negative resistance, see what the error was in your math. Okay? One final thing I'd like to say about Thevenin's theorem, and that's this. Thevenin's theorem, and this may or may not, hopefully this is kind of obvious to you, but Thevenin's theorem is always a function of which two nodes you are taking the Thevenin equivalent circuit across. Okay. I've got nodes A and B I'm pulling out here. Over here, I've got nodes C and D. The Thevenin equivalent circuit between A and B is going to be different than the Thevenin equivalent circuit between C and D. And you think about it, that makes sense. If I put a resistor between A and B, certainly I won't have the same voltage or current than if I put it between C and D. You're connecting it in a different spot of the circuit. So Thevenin's theorem is a function of which two nodes you choose to connect your load across. Once again, hopefully kind of an obvious thing, but something that bears repeating just in case people are confused about it. All right? So that kind of wraps up everything we need to know with Thevenin's theorem. Really, this all comes down to understanding how to use the techniques to find VTH and RTH, and also being skilled in either mesh or nodal analysis in order to solve these circuits. Other than that, it's pretty straightforward, and the best you can do is simply to practice the problems until it's a great way to develop your skills in nodal or mesh analysis. And as I said before, it's a very important theorem in electronic circuit design, and certainly you need to know it. All right? So next time we'll wrap up and we'll briefly discuss Norton equivalent circuits and Norton's theorem.